Good morning, everyone. Today we're going to continue on with Chapter 7. This will be section 7.5. It's on the inverse functions for the trig functions. We call them inverse circular functions. I wanted to remind you how inverse functions work. Inverse functions they are one-to-one functions. One-to-one functions. Pass both the vertical line test and the horizontal line test. Okay. What this really means is there are no duplicate y values or x values. Examples in regular algebra, f of x equals x cubed is 1-to-1. F of x equals x squared is not. I'm going to edit this one a little bit. Got Desmos open to do some illustrations for you. Now notice if we look at the graph of sine, this is y equals sine x. Y equals sine x is not 1-to-1 as is. The x values don't repeat, but the y values do. Every time we go through not even a full cycle, as soon as I go from 0 to pi over 2 and I start coming back down again, my y values start repeating. So this is bad the way it is. But we can make trig functions 1-to-1 by restricting their domain. Now, I don't want my y values to repeat. And so we have a lot of options. We could go from pi over 2 down all the way down here to 3 pi over 2. And our y values go from 1 to -1. That's not the custom. We try to stay as close to 0 as possible. So we're going to start at negative pi over 2 and go up to pi over 2. Notice that covers the full range of sine's values, -1 to 1, without any repeating on those values. So I actually have that listed in here. And now if we look at it, my y values don't repeat. So this is y equals sine inverse x. Let me put it in the notes. We've got y equals sine x. We've got 0, pi, 2 pi, negative pi, negative 2 pi, -1 and 1. I'll put my midpoints. That's part of my normal graph of sine. And when we want to restrict it to being 1 to 1, which I'm going to do in red, that's my domain restriction. So we restrict it from -π/2 to π/2. That's the domain for sine when we want to work with the inverse functions. Let's take a look at cosine. Also repetitive. We want to stay as close to 0 as possible. If we try to do -π/2 to π/2, our y values repeat. So the way we end up restricting cosine is we start at 0 and we go to pi, and that'll cover the full range. And if we look at it now, that's what it looks like now. Our y values do not repeat. So I'll do this on another page. Pause it if you need that up longer. Okay. So let's look at cosine x on paper. We restrict the domain to be between 0 and pi. So I'll do that part right here in red. So that's my domain restriction. Domain of cosine will be 0 to pi. And if we continue the graph on, it keeps going cyclically. Oh, I'm off the screen. And tangents is pretty easy to see. Remember, tangent has those asymptotes at all the odd values of π/2. That's when the graph starts repeating. And other than that, it doesn't repeat. So when we have y equals tangent x, just sketching some out for us. We've got asymptotes. made that kind of wide over there. So our red one will be our domain restricted one. We want it as close to 0 as possible. X value is close to 0, so we're going to use that one. So the domain of tangent is negative pi over 2 to pi over 2, but we don't include them because those are asymptotes. And our regular tangent just keeps going doing the same thing, but like such. So we restrict tangent to that. And we take a look at it. And we just get one graph. All right, so those how we restricted. Let's start looking at the inverses. Actually, I want to point out another thing for you. You might find it handy. Looking at the unit circle can help. That is not too bad of a freehand circle. Remember, we have A, S, T, C. All strippers take cash. And the idea is we want to restrict. We want one positive region and one negative region. For each trig function. So for sine is greater than 0 up here, less than 0 down here. So we use this region for sine. That'll be our sine domain. And you can see that's negative pi over 2 to pi over 2. Same thing goes on with tangent. So that's tangent's restricted domain, but we don't include the endpoints because they're asymptotes. And if we look at cosine, cosine is greater than 0 here. Cosine is less than 0 over here. So we restrict cosine to be that region. And you'll notice that goes from 0 to pi. So we just want one positive and one negative region for each trig function. The unit circle can help you find it really easily. And it makes it memorizing it a lot easier, to be honest. If you understand what's happening, it's easier to understand. All right. Pause this if you need this up longer. Okay. Okay, so how do inverse functions relate to the base functions? So if f of xi, I'm sorry, not f, if xi, yi is on f of x, so xi is just some value, yi is another value, could be the same, might be different, could be the same. Then xi are on f inverse. And in normal words, the domain and range swap between inverses. Or flip, that's another way of looking at it, they flip. And how did we find inverses in algebra? To find the inverse of f of x, we had several steps. Step one, we replace f of x with y. Then we swap x and y. Once you've done that, solve for y. And finally, replace y with f inverse of x. The negative 1 is not an exponent. When it's indicated on functions like these. Only on a variable will it mean an inverse. Or is it an exponent? For example, x to the negative 1, that is an exponent. It's not an exponent if we have something like this, sine inverse of x. So let's see what happens with sine. So we start off with f of x equals sine x. I'm going to replace f of x with y. Then I'm going to swap my x and y. And what we're effectively doing is taking sine inverse of both sides. when sine inverse and sine cancel each other out. Kind of like natural log and e canceled from algebra. Remember when we had that? We took the natural log if we had an exponent to get rid of the e. Same idea. And what we end up with here is y equals sine inverse of x. They write this two ways. You'll see this different ways. So they'll write sine inverse like that. Another way they write it so that it's clear it's not an exponent, they call it arc sine. Same thing. It means the same thing. So we started with x equals sine y. We end up with this. What this says, notice if we look at it from here, y is the angle in the interval whose sine value is x. That's how it reads. So when you see y equals sine inverse x, what we're saying is what angle do we got to plug into sine such that we get x? I thought I'd show you sine and its inverse. There's sine inverse. Notice my x and y values swap. Here, this was pi over 2 comma 1, and now I've got 1 comma pi over 2. 1 comma pi over 2. Oh, it doesn't want to show pi over 2. That's pi over 2. Same thing down here. The other thing this is saying, how our restrictions fit in, negative pi over 2 is less than or equal to y, which is less than or equal to pi over 2. And we can see that right here when we just look at the sine inverse graph. We got negative pi over 2 to pi over 2. Our domain is restricted from negative 1 to 1 for sine inverse. That's how we're able to use inverse trig functions. And they're handy when we know the value that we need, but we don't know what angle goes in there. So I just showed that. Let's say it again. Y equals sine x. The domain, we do negative pi over 2 to pi over 2. The range was negative 1 to 1. And when we have sine inverse, they swap. Now the domain is negative 1 to 1, as we just showed up here. And the range is negative pi over 2 to pi over 2. The other properties of inverses, There we go. I like it dotted. If we look at it right here, this green dotted line is y equals x. And so that's the other property. It's a graphical property of inverse functions and their base functions. F of x and f inverse of x are reflections of each other across the y equals x line. As we can see in our Desmos image right there. Let's take a look at sine. I think I said sine, I meant cosine. So there's my base function for cosine. Where's my cosine inverse? Can I just type it in? Maybe I can use it right here. There we go. Let's see functions. Cosine and its inverse look kind of neat, don't they? Kind of looks like bull horns sideways, like the bull's all tipped his head sideways. But we can see they're reflections of each other across this line. And let's take a look at this. The blue function was cosine. So if we look at the domain and range of cosine versus cosine inverse, y equals cosine x. The domain was 0 to pi. The range was -1 to 1. Cosine inverse of x, the domain is -1 to 1, and the range is 0 to pi. And finally, we can look at tangent. Now you can really see that mirror property. Let me turn off one of them. Let's turn off the inverse real quick. So if we look at tangent, our domain, we couldn't have pi over 2 or negative pi over 2, but we had all the values in between. And the range on it, if we keep zooming out, out, and out, and out, it keeps going up and up and up, or down, down, and down. The range is -∞ to infinity. Which means tangent inverse swaps those. And the range is now negative pi over 2 to pi over 2. And we can see that here. The domain just keeps shooting left and right but it never goes above pi over 2 or negative pi over 2. Get comfortable in my chair. All right. Ready to look at some examples? So examples. My notes out of order for you guys. That's no bueno. There we go. So find y if it exists. A, we're going to do y equals arc sine of root 3 over 2. I think the easiest way to do this is really rewrite it in its other form. This says the sine of y equals root 3 over 2. Where does sine equal root 3 over 2 between negative pi over 2 and pi over 2? Or negative 90 degrees to 90 degrees. Well, at 30 degrees, sine is 1/2. At 60 degrees, sine is root 3 over 2. So y equals 60 degrees, or what is that in terms of radians? That's pi over 3. It's pretty straightforward, right? Pause that if you need it. Let's look at some more examples. Y equals sine inverse of 1. Translation, sine of y equals 1. Where does sine equal 1? It actually only equals 1 at y equals 90 degrees or pi over 2. That is in our domain, so we can include it. So that was example B. Example C, y equals sine inverse of 4. Would you take a second and see if you can work that out? Okay. What we're really saying, sine of y equals 4. If we look at the unit circle though, sine is restricted between -1 and 1. Or if you think about it, we had negative pi over 2 was less than or equal to y, which is less than pi over 2. This is 3.14 over 2, which is about 1.57. And 1.57 is less than 4. 4 is outside of the domain of sine inverse. So you can say a couple ways people say it. They say no answer, no solution. I'm particularly fond of DNE. It takes the least amount to write, and it means does not exist. All right, that's sine. Let's do three of them for cosine. And I want you to work them out real quick. Y equals arc cosine. Arc cosine has two C's. That'll be A. B. C. Pause for a second and work on that if you need to. Please do. It's good practice. I can show you how to do it, but you're not going to learn it unless you try. This says cosine of y equals -1. Remember, for cosine inverse, we have 0 is less than or equal to y, less than or equal to pi. Cosine equals -1 at pi. So y equals pi, or 180 degrees if you're working in degrees. That says sine. I want cosine. Cosine of y equals -2. -2, so the range on this is -1 to 1. That -2 is outside that range. So dne. And finally, we have cosine of y equals 1/2. And we want quadrant 1 or quadrant 2. Only in quadrant 1 is cosine positive, so we're looking at 0 to 90 degrees. And the angle where cosine equals 1/2 is 60 degrees. I think you get the idea, right? Pretty straightforward. What about the reciprocal functions? So I'm going to put cosine in real quick. Turn off tangent. And what does secant look like? Maybe I need secant in there. That's probably the better one. Secant has these weird things. Remember, it's related to the cosine graph. We don't want y values to repeat. So if we go from 0 to pi over 2, and then pi over 2 to pi, The 0 to pi over 2 covers all of the positive values. Pi over 2 to pi covers all of the negative values. And if we look at the inverse, it's crazy looking. So secant x, we're going to go, x is, we can do 0 less than or equal to x less than or equal to pi, but x cannot equal pi over 2. That's an asymptote. That's our domain. Our range, we put it back up, looking at secant. The small, it goes from 1 to infinity and negative infinity to negative 1. It does not hit anywhere between negative 1 and 1. Negative infinity to negative 1 in union with 1 to infinity. So secant inverse is going to swap that. The domain is crazy. It can't, it goes up to negative 1 and it stops and it restarts at 1. But it can equal 1. The range is 0 to pi. It doesn't equal 0. Well, yeah, it does equal 0. It does equal pi, but y cannot equal pi over 2. That's an asymptote. So when we swap x and y values, the asymptote changes. So that's secant. Notice same range restriction. Same restriction as cosine. We want 0 to pi. So let's look at cosecants rules and then cotangents. Pause the screen if you need that up longer. Okay. So we've got cosecant. Cosecant x is similar. Its x values go from negative pi over 2 to pi over 2. But x cannot equal 0. And that was our domain. The range also had that crazy domain, negative infinity to negative 1, in union with 1 to infinity. When we swap it with switch to cosecant inverse, these two swap. The domain is now in negative infinity to negative 1, in union with 1 to infinity. And the range is now negative pi over 2 to pi over 2. And we don't want y to equal 0. Those are our asymptotes. Cosecant and sine have the same restriction. Negative pi over 2 to pi over 2. And that's what the graph of cosecant looks like, cosecant inverse. And finally, let's take a look at cotangent. Cotangent goes from 0 to pi. We're going to restrict our domain to be between 0 and pi. That's where it's not repeating. As soon as we get to pi, asymptotes are at x equals 0, x equals pi are asymptotes. And after we get past pi, it starts repeating. The range is negative infinity to infinity. So when we look at cotangent inverse, we just swap them. The domain is now negative infinity to infinity, and the range is 0 to pi. Or 0 to pi. Notice it never actually touches 0. It gets close. It gets close, but it never actually touches. And here, the asymptotes are y equals 0, y equals pi, are asymptotes. So I guess we could say y can't equal 0 and y can't equal pi. What was tangent's restriction? Tangent was restricted to negative pi over 2 to pi over 2. Cotangent, 0 to pi. They have different restrictions. They're the only two reciprocals that do, which makes working with cotangent inverse a pain in the ass. I'm going to be honest with you. You will rarely ever use secant inverse, cosecant inverse, cotangent inverse. So much so, I won't test you on those three. But you should do the problems so you get some practice with them. For the times they do pop up, you need to at least have some experience in your life working with them. Kind of like riding a bike. Once you figure out how to do it, you stop riding a bike for a long time, you get back on a bike, you're a little clumsy at first, but you can figure it back out. You may have to relearn how, like a 10-speed, the gears shift and stuff, just like you'll have to relearn how to do these, but you've done it before, you know what to look for. All right, so let's look at other stuff related to these. On calculators, when it's not one of our easy to use trig values, one of our 5 basic ones, finding the inverse on a calculator that have trig functions is always easy for sine inverse, cosine inverse, tangent inverse. It's straightforward. Maybe not easy, but straightforward. And we'll work on doing that in just a second. Not all calculators, not all scientific calculators have inverses for the reciprocals, though. Have inverse keys for secant, cosecant, and cotangent. And we'll address how to do that in a second. This entirely just depends on the calculator. Mine doesn't have it. If yours has it, it's going to be easier. I'm going to show you how to do it on the ones that don't have it, because that's what I've got. Pause for a second, let you write that down. I hope looking at Desmos helped out. Seeing the shapes of those graphs is kind of helpful. Find theta if it exists. A. Theta equals arctangent of root 3. Hopefully by now you're feeling comfortable going, maybe I should rewrite this and say tangent of theta equals root 3, and where does that occur? We look at our tangent function, theta has to equal 60 degrees or pi over 3. Theta equals cosecant inverse of -2. You don't always need a calculator. What is this telling me? This tells me that cosecant of theta equals -2. But what is cosecant of theta? That's telling me 1 over sine theta equals -2. And I flip these, this tells me sine theta equals -1/2. Where does that occur? Well, sine of 30 degrees is 1/2. So sine of -30 degrees is going to be -1/2. Theta equals -30 degrees or -pi over 6. This approach is actually how we do it for the weird ones. So if I want to say theta equals let's do secant. Secant inverse of -3. This is telling me secant of theta equals -3. Which means 1 over cosine theta equals -3. So cosine theta equals -1/3. And now check this out. Now let's turn it back into inverse form. Theta equals cosine inverse of -1/3. This is a calculator operation. I don't know where that happens. So can you see my cosine key? See how it says cosine -1 above it? Sine has the sine inverse, tangent has the tangent inverse. I have to access them with my yellow key, which is shift. So I am going to say shift cosine. Notice it spits out cosine inverse. Parentheses, -1 divided by 3 in parentheses. This is in degrees, I'm pretty sure. Yeah, it says D. That means I'm in degrees, which sucks. So theta is approximately 109.47 degrees. Is that in cosine's range? Yeah, it's 0 to 180. I can switch this over to radian mode. So on my calculator, if you have one similar to mine, I have to hit mode, and then I hit mode again, and I can get to radians by hitting 2. And now this D changed to an R. And I can do cosine inverse of -1 divided by 3. And it gives it me 2 in radians. Theta is approximately 1.91 radians. So that's how we will do the secant inverse and cosecant inverse. Cotangent is a little trickier on a calculator. So hopefully you hit pause and write this stuff down. So cotangent inverse of X is trickier on a calculator. Because, and it has to do with those restrictions. Tangent inverse and cotangent inverse have different domains. So in a calculator, cotangent inverse of X, it's got two things going on. If X is greater than 0, we're just going to treat it as tangent inverse of X. If X is less than 0, we're going to treat it as 180 degrees plus tangent inverse of X, or pi plus tangent inverse of X. My lecture notes. Every once in a while I find an error on them, and I just did. So try these on a calculator. Let's do a cotangent inverse on the calculator. Let's do theta equals cotangent inverse of -0.4279. Here, x is less than 0, so I'm using the second option. So I'll switch this to cotangent. Which I'll write as 1 over tangent. I wish I knew how to turn that off. It's irritating that Google Chrome does those. I'm gonna have to look at the settings. So this tells me I flip them. Tangent theta equals negative or 1 over, I guess I can put the negative out front. And we'll switch to the inverse. Theta equals tangent inverse of negative 1 over 0.4279. But we need to add pi, plus pi. So this might be easier to do. Am I still in? I'm still in reading mode. Okay, good. I'm going to do 1 divided by negative 0.4279 and the equal. And now I'm going to say shift tangent inverse of the answer. That pulls up the last answer I had. So that's our first step. Negative 1.166 plus pi. Plus pi. So theta is approximately 1.975. And these were both in radians. Of course, if you need to do it in degrees, do it in degrees. We still got more to do in this section. This is actually a kind of long section. A lot of it you won't use very often, which is why I'm not testing you on it, but you need to have seen it. All right. A couple more types of problems we will do. We're going to, in the following problems, evaluate without using a calculator. And I actually like these problems a lot. Once I learned how to do them and what was going on, I think they're really cool. I hope you feel that way too. Cosine of tangent inverse of 3 over 2. Okay, so what I'm going to do is I'm going to call this theta. So theta equals tangent inverse of 3 over 2, which means tangent theta equals 3 over 2. And what do we know about tangent? When we draw it, it equals y over x. We know tangent is restricted. Negative pi over 2 is less than or equal to theta, which is less than or equal to pi over 2. Here it's positive. Positive. This is quadrant 1 and quadrant 4. Negative pi over 2 to pi over 2 is quadrant 1 and quadrant 4. Positive tells me I want quadrant 1. So I'm going to draw a picture in quadrant 1. My y value is 3. My x value is 2. And that's theta right there. You with me? So we make this interior thing equal a degree. Then we write it as its inverse. We swap them over. We identify the quadrant it is based on the domain restriction. Draw a picture. That's theta, and I need to find cosine of theta. Cosine of theta is x over r. I've got x. That's 2. I don't have r yet, but that's r. And I can use the Pythagorean formula. R squared equals 2 squared plus 3 squared. R squared equals 4 plus 9. R squared equals 13. R equals the square root of 13. R is always positive. We don't need to worry about the negative root. So cosine theta equals 2 over root 13. And if we want to be proper, we'll move the radical to the top by multiplying top and bottom by it. I think that's kind of neat. It's a useful, really useful skill in calculus when you get there. Being able to do these pictures and switch these inverses and figure out what's going on, draw the picture of what's going on. All right, let me give you guys one to try. Cosine of sine inverse of negative 5 over 13. Click pause and work on this problem. All right, I'm going to assume you did. I'm going to label that theta. Here we've got negative pi over 2 is less than or equal to theta, which is less than or equal to pi over 2. So sine of theta equals negative 5/13. This is quadrant 1. Oops. Yeah. Quadrant 4. The negative 1 tells me we're in quadrant 4. That's where sine is negative. So when I draw my picture, I'm going to go downward. I'm going to draw it in quadrant 4. Sine is y over r. I don't know how far that x value is. This is x. This is negative 5. That's 13. That's theta. So again, cosine theta is x over r. I have r. R is 13. What's x? I've got x squared plus negative 5 squared equals 13 squared. X squared plus 25 equals 169. X squared equals 144, which means x equals 12. Which means my picture's kind of bad. Maybe it should have been more like this. So cosine theta is x over r, 12 over 13. Your initial sketch always isn't great, but it at least tells you how to label a triangle. It may not be accurate, like my first triangle was garbage. My x thing was way shorter than my y, even though it turned out x was 12 and y was 5. More fun. Oh, you're gonna really like this. This is the good stuff. Are you doing it? Are you going woo woo? I know you are. I know you are. You're all excited. All right. Let's take a look at find the value using identities. Sine of tangent inverse of square root of 3 plus sine inverse of 1/3. I guess I don't need Desmos anymore. Let's just turn off that picture. So this is a lot like sine of a plus b, where a equals tangent inverse of root 3, and b is sine inverse of 1/3. So this tells me tangent a is root 3, and this tells me sine of b is 1/3. These both have the same domain restrictions. And they're both positive, so they're both in quadrant 1. So I need to draw a picture for A and B. A, tangent is y over x. So my y value is root 3. My x value is 1. And that's angle A. Maybe we should figure out what R is real quick. I'm sure we're going to need it. I've got R squared equals 1 squared plus root 3 squared. R squared equals 4, so R equals 2. I'll put that in my picture. We look at B. This is y over r. I don't know how far out x is. That's B. This is 1, and we've got x, and r is 3. So I've got x squared plus 1 squared equals 3 squared. X squared plus 1 equals 8, or 9. X squared equals 8. So x equals the square root of 8, which is 2 root 2. Okay, so I've just figured out what my angles look like, and I can get all the trig values now. So sine of a plus b, what was the formula for sine of a plus b? You remember? Sine switched values. We had sine a cosine b, and then we had cosine a sine b. So what do we have here? I have sine b already. This is 1/3. That was given to me. I need to figure out my other values. So sine A is y over r, which is root 3 over 2. Cosine A is x over r, which is 1/2. And finally, I need cosine B. And that's again x over r, which is 2 root 2 over 3. And I will put these all in up here. This is root 3 over 2. Cosine B is next, 2 root 2 over 3, 1/2. Now it looks like the 2's cancel out, but then I have different denominators. Right now I've got a denominator of 6 on both of them, so I'm going to leave it. So if I multiply that out, the root 3 and the root 2 multiply together, that gives me 2 root 6. And this one's numerator is 1. The denominator is 6. And you're more than likely going to see it in this form. We tend to like to put the radicals at the end, because that way there's no mistaking that nothing that follows it could possibly be underneath it, because there's nothing after it. Pretty crazy, huh? But wait, there's more. I'll let you pause and finish writing this out. All right. Let's kick it up a notch. I've got sine of tangent inverse of u. We're going to do what we did before. We're going to call that theta. So theta equals tangent inverse of u. And tangent theta, recall, is y over x, is u. I don't know, is u greater than 0? Is u less than 0? I don't know. Which means my picture has a couple options. If I say x equals 1, I can do it like that. And we've got a y value of u, which could be positive, it could be negative. So I'll call that theta 2, and this is theta 1. I don't know which triangle applies, so I need both. I'm looking for sine. Sine of theta is y over r, so I need r here. My x value is u, so r squared equals u squared plus 1 squared. So r equals the square root of u squared plus 1. So I have sine theta is y, which is u, over the square root of u squared plus 1. And remember, we're restricting theta still. And this doesn't matter. This works whether I'm using theta 1 or theta 2. What's the difference? On theta 1, u is greater than 0. Does that match up with what we have? This means we're in quadrant 1, and sine theta needs to be greater than 0. Is it? Well, if we look at it, if u is greater than 0, sine theta has a positive value on top because u is positive. U squared plus 1, something squared is always positive. And even if u is 0, 0 plus 1, this denominator is always positive. So sine theta is positive. And it matches the greater than 0. For theta 2, u is less than 0. And that puts us in quadrant 4, which means sine theta needs to be less than 0. And let's check it. Sine theta is u over u squared plus 1. We just got done illustrating the bottom is always positive there. We said u is less than 0, so it's negative. And this makes this whole thing negative, which is less than 0. So it meets there too. This formula works for either one. We might have had to introduce a negative sign if something didn't match up, but it works for either one. And finally, we would likely rationalize. So we've got sine of tangent inverse of u I multiply the top and bottom by the square root of the bottom. Ready for more? Got one more problem. We're almost done with the section. This has been a long section. I've got cosine of 2 sine inverse u. I think it's easier right here to make theta equal just the sine inverse. So sine theta equals u. So I've got cosine of 2 theta. That has a bunch of forms. We had cosine squared theta minus sine squared theta. We had 2 cosine squared theta minus 1. And we had 1 minus 2 sine squared theta. One of these is easier than the other two. I have sine theta is u, which means sine squared theta is u squared. And I'll plug it into that one. Cosine of 2 sine inverse of u is 1 minus 2u squared. Good stuff. I think it's pretty neat. That'll end up 7.5. I will make 7.6 shortly. I'm gonna go eat breakfast. Say good morning to my wife and my dog. I hope you enjoyed this. Remember, you're not gonna be tested on the reciprocal functions. You do need to know how to graph the inverses for sine, cosine, and tangent. You need to know how to do a bunch of these problem solving things that we've just done. You need to be able to find the inverse values for the functions. Graphing them for the reciprocals, no. Should be able to work with the reciprocals, but and that'll be it for this section. Peace.